Hi there, you're right, it's Tommy Allen here, and today I want to go through with you my C++ code for an occlusion system and early reflection system at the same time, and how I've built it. So first of all, I built this game in code. It's a simple little third-person shooter where basically an enemy finds you, shoots you, and your health goes down, and the aim of the game is to kill all the enemies. Okay, and within this I have built an occlusion system. So let's take a look at how that is done. So in my first player character, I have this C++ class in here called acoustic player balls. So the first design was actually made with kind of balls all floating about the area. But then it ended up changing, but I never changed the name. But this is how it works. So I'm going to turn on debug lines, and basically you can control the azimuth angle and the elevation angle and the trace radius from within the game. So when I press play, I have a bunch of these traces that are going to detect where things have been hit. So at the minute, the red lines are where it is hit, and the green lines is where we don't get hits. Okay, so within this blueprint, we can actually alter the offset. So if I put this to 75, it will be round its head now. I can change down the distance to about 300. The trace range 300, and the no hit distance I'm going to put at 100, and you can see how this works now. So compile. So what is now happening, okay, if the ray does not manage to meet a surface, it has 100 meters going around the player, or well 100 centimeters, and if it does hit, okay, then we get a nice red line. So if we come closer to the wall, we can see our lines actually hitting. This is all going to make sense in a bit why this is happening. But basically, we usually have them set at a much larger radius. Okay, let's put this to 1,000. And we can change the azimuth angle. So if there's too many rays, because we want to make it more efficient, okay, we can change the angles of what they're kind of being done at. And now we've kind of only got a few rays going around our player. Okay, so greens are hits. Oh no, reds are hits, and greens are where they don't hit. So outside that window, we get no hit. Okay, so in the thing, I'm just going to turn my no hit up to about 300, because that's where I seem to like it. And I'll change these back down to 45 and 45. And so what's happening, okay, is every single place it hits in the game, it's going to give us a bunch of data, which we're actually going to use later for the early reflection system, but just to show that it's there, it should print on the screen now. So as we move about, we're getting our elevation angle, our blocking hits, actor name, physical material, and we can be able to use that later. So let's turn that off. Debug lines off. And so that's the first part, okay? So the idea of this is where everything hits. So these lines are kind of what you can hear around, what you can see, what you can, kind of your audio eyesight, because you can hear around corners and things like that. So on this actor here, this blueprint, it's just a little ball. We've got a source A, B, C, D component, or that's what I've called it. There's a few iterations for the names. And when we turn this on, I'm going to put on the debug, and we'll be able to see it in action. Okay, so we've got a ball that plays music now. And okay, look quite messy. So if I just bring these debug lines down a little bit, so I'm going to go down to here, make it just so it's really obvious for everyone what's actually happening. Okay, so now as you can see, the ball that's playing the audio is now firing traces to where our possible audio space of what we can hear in. Okay, this isn't probably what we normally use, but this is just for demonstration. And when we go behind the wall, it gets quieter and quieter until none of them are hit. Okay, but usually we'd have the lines extend a lot further. And what this is doing, it is controlling, it's gone, the volume multiplier. Okay, so we've got about half of the object is visible. Ooh. Gotta pull out, come around here. And as you can see, the volume multiplier has now changed. If I lock this in the panel and we move about, it changes our volume multiplier down here. Okay, just doesn't move down, not 0. So we make that a bit more realistic. I'm going to turn off the debug lines for here. The debug lines are on. Let's make this 1000. A bit more realistic. 300. Compile. Okay, so that's the first basis of the occlusion system. Okay, so you kind of make this a bit more efficient because we're doing a lot of ray traces. Okay, what we actually have is this is only active when the audio is playing. So if we turn the audio off on our ball, we're going to get no traces. Okay, so it's only going to work when the audio is being played. If I now come into this little player character, it also has source A, B, D, C attached to it in the player character blueprint. I've attached to the gun is the same kind of component, and it has, I'm going to stick on the debug so you can see, and only when the sound is active will we get the ray tracing happening. Okay, so as you can see, these are the debug spheres that we have to enter for it to start happening. Okay, so we are now in the player that's going to shoot a sphere. Or now we are. So now when he shoots us, okay, we get out of his sphere, it turns off. Okay, this is quite a short sphere, but just for demonstration. And then it's only active when he shoots, so when audio is actually playing. He's going to find us. Excellent. Run away from him, get out the debug sphere, and it's now not active. So it's only when you're inside the sphere to make it a bit more efficient and working as is. Okay, and that also changes the volume multiplier. So that is the first part of the occlusion code. Parts in the next... Oh, no, there's one more part as well. So what we have... I'm going to go back to the blueprint. So, gun blueprint. Because it's trying to find... Is the line... Hold on, I'm going to turn on the debug to make it hyper clear. Turn on debug lines. Okay, so there's quite a lot of lines going on. So as you can see, right, some of the surfaces are quite uneven. So in this case, I've actually got a tolerance distance. So if it hits an uneven surface, where it doesn't exactly hit, but you would probably get a reflection, okay, or an occlusion part, we have a tolerance distance. So let me just pause this. Okay, and I'm going to try and show you what I mean. So inside of this, on this source ABCD, I've got tolerance distance. If I turn this down to 0 and it starts hitting against surfaces that it doesn't hit, okay, we're going to get a lot of things where it should hit, but it's not hitting. Okay, here's a good example. So this line here is coming down to this line here, and it's red. But really, it can see it is hitting, but because it's not exactly in the actual, it's not hitting the exact spot that this ray tracing is going to, we get a no hit. So for this case, what we have is a tolerance distance, which kind of acts a bit like a ball. Okay, so if I put 100, we've kind of, it's quite a lot really, we just need 10. So in that case, we've got a 10 centimeter ball. So if it hits anywhere in that radius, we should now get a successful hit. Okay, this isn't really for the occlusion, but this is going to be used for later. Oh, I'm hiding everything. So now you can see it is actually successfully hitting around the dodgy parts. Okay? Oh, go away. So what the tolerance distance does is just kind of give it that extra little bit of, it's extremely close, let's call it a hit. Okay? Yeah, so that is the kind of the first two parts of the code. We've got this on the player shooter, we've got this C++ class that kind of gives us where we can hear, what audible things, what is our actual space. And then on the other classes, we have a source ABCD that then fires rays to those, can it see what we could hear? Almost. So they're the ray traces that we are using. Okay, so in the next part, I've showed you the quick occlusion system. Now, in the next bit, we're going to look at, so we've got a tap delay manager. Okay, this is going to be used for early reflections, because with all the data we've got there, we have the information to start producing early reflections, and also how we can run them. Okay, so also we'll use this ball. I've got a custom audio component that then will actually allow all the audio that is based on this actor to run through all our target submixes and tap delay effects as they update in real time. So I'll see you in the next one, and I hope you enjoyed that.